Good afternoon, my dear student friends. Yesterday we were discussing about the problem regarding the application of control charts for attributes. Okay, I'll take up the same problem because it was not done fully. We could identify which type of chart is to be used, and then we calculated the control limits. But another question regarding the 26th, what is the probability that the 26th lot will contain 7 defectives exactly or more than 7 defectives? You got that problem? The problem goes like this. The item is made in lots of 200 each. The lots are given 100% in inspection. The record sheet for the first 25 lots inspected showed that a total of 75 items were defective. Determine the trial control limits for NP chart showing number of defectives in each lot. Second, assume that all the points fall within the control limits. What is your estimate of the process average fraction defective P prime? Third, if this P prime remains unchanged, what is the probability that the 26th lot will contain exactly 7 defectives and that it will contain 7 or more defectives? Because since we could use the NP chart as the sample size was fixed, it was fixed at 200 items. 200 items, the sample size was 200, and we could find out what is the P bar. P bar we could find out because the total number of defectives found were 75 and the total number of the items inspected, that means 100% inspection means all the samples in the lots are to be inspected. Okay, so that means 75 divided by 200 into 25, so that we calculated as P bar is equal to 0.015. Okay, and he says, because one more thing you try to keep it in your mind, determine the trial control limits. Why he had used this word, trial control limits? Because based on whatever the 25 distinct lots he has considered, based on that one he had established. Okay, and if all the defectives or the fraction defectives, they fall within the control limits, then it will become standardized. Till that time, whatever the control limits we are going to establish is called as the trial control limits. And once it's standardized, then it will become the standard control limits. Now, the last one, because other things have been calculated, the last thing, because I was discussing about how to find out the probability that the 26th lot will contain exactly 7 defectives or 7 or more defectives. Well, as I was explaining, it follows the binomial distribution. But here in this case, we can directly find out by using the binomial distribution, or we can approximate it by the Poisson's distribution. So I will try to calculate both of them so that it becomes more clearer for you in understanding the things. Otherwise, simply we will say that when n tends to infinity, p tends to 0 and other things, it may not be that much appealing unless we take up some example and carry out the experiment. It is sort of the experimentation that has been carried out just like that. Okay. So now the things are what? Now we know that P bar is 0.015 and we know n is equal to 200. So if you look at it, because just for our purpose now it is finding out the probability. Well, let us forget about control charts, limits and other things we have found out already. Now we want to find out what is the probability that 7 defectives, and the second thing, probability that the x will be greater than or equal to 7 defectives. We need to find out. How to find out this one? Because that means what? Actually, we take a sample of 200, okay, on an average, which consists of 3 defectives. Three defectives on an average, because n into p. Okay, average, because it doesn't mean that always you should contain 3 defectives only. Not necessary. It may contain 1 defective, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12, up to how many defectives it can contain, you can just think. It may contain all 200, or how long we'll go on finding out that one. That is to be understood. Okay? That is the idea behind this one. Why he has asked us to find out what is the probability that it contains exactly 7 defectives. Why not 3 defectives? Why not 0 defective like that? We need to understand those things. And when we have drawn or calculated the control limits using the NP chart for this, we said the upper control limit is 8. That is what we said. Upper control limit was found out to be 8. And the lower control limit, we found out to be 0. That means most probably, if it is under control, the maximum number of the defectives you can expect is 8. They should not produce more than 8. That is why intelligently he has asked what is the probability that it contains 7 defectives. If it is 9 defectives or 10 defectives, it goes on reducing. That is what we will try to find out, and then try to establish those things. What is going to happen like that? So now, since it follows the binomial distribution, if we want to calculate it by binomial distribution, how it can be calculated? For that purpose, we will be using the equation probability that the random number, namely here x, I define as number of defectives and in this case 7 defectives or more than or equal to 7 defective like that. That is the small x, that is what it means. So this capital X, whatever it is, that means I should mention this one as x will take a particular value. That means remember, random variable will be denoted by capital X, and particular value it takes is denoted by the small x. So we are interested in finding, that means it will give us okay. He will be collecting, one will be collecting, what is the probability that how many ways I can collect X items out of a total number of, how can I select X items out of a total number of N items. This combination and P, defective, fraction defective. It is not good number of items, because whichever is the least, that one we consider it as P. One more thing we can learn from this one is, whichever is less, whether good item is less, or good items are less, or the defective items are less. Naturally, the defective items are less. So that is what we are interested in finding out. That is what he has asked, number of defective, that is what I had defined, random variable. That is why P should correspond to that. If I define this one as good items, then P corresponds to that one, good items. Okay? So now here it is corresponds to the defective item. That is why that P of fraction defective, that is what P. And this is equal to NCX P to the power X into Q to the power N minus X. fraction of good items. And we know both P plus Q will be exactly equal to 1. When we know the P, here we know P as 0.015. Hence, Q is equal to how much? Q minus 0. So this will, okay, what this one? Yes. Now exactly it gives the value. That means I'm interested in N is 2, C, P is 0.015 to the power 7 into 0.985 to the power 200 minus 7 works out to be about 0.02. Okay, that means roughly around 2%. The probability that we are going to get exactly 7 defective is 2%. Okay, because here now it is average, this thing is 1.5% defective. That is what it means. Now, how do we find out the probability that X will be greater than or equal to 7? That means I need to find out what? I need to find out X is equal to 8 plus how long? That is the thing. We'll go on extending up to what? Maximum we get exhausted at 200. All the items will be inspected if they contain those many defectives. Okay? So if we look at this, it behaves like this. We don't know. Then what is the way out? Because it is going to take us more time now. Instead of that one, we'll be going for the complementary event. That means if I break it up, okay, this is what? Probability that X will be than the same thing, I can break it into different way. How I'll break it? Now I'll look at probability that X will be less than or equal to 6. Okay? But it cannot be lesser than that one, you try to understand, because it is, that means X will be varying between 0 to 6. Okay? Probability that is greater than or equal to 7. It's put together at 0 to at whatever value infinity. That is going to be 1. Is it not? This one plus this one should be 1. Now, I will transpose these things. Therefore, P greater than or equal to 7 should be equal to 6. This one. It is as simple as this. So, if I have to find out this one, less than or equal to 6, then I need to calculate. That means I need to find out probability that X will be less than or equal to 6 equal to probability that it is 0 plus 1. Writing these probabilities here inside the bracket. 4 plus 6. So I need to find out this. Like using this equation. For example, probability that it contains 0. So these things are to be calculated. I can give you the value which works out to be 0.0486. Okay? 0.0486. Similarly, I can calculate for one n minus x. So it works out to be 0.148. Okay? Similarly, because in that case 200 C 2.015 to the power 2.985 to the power 198. So that works out to be, or all the values I can give you here, these calculated values. So it works out to be 0.2245. Similarly, P of 3 is going to be point 0.010. P of 6 0.05. Is it understood? So just try to observe over here. Now the probability, what is happening? It has gone on increasing up to this point where P of 3. 0.2245, this is 0.2257, afterwards it started decreasing. This is what the peculiar nature. That is what, even if you normal distribution and other things, that is what it increases, decreases, or even if you draw like that, that is what it is going to happen. That means the mean value is how much here? Mean value is around 3. This is the maximum probability that it occurs. That is going to be the mean value. That is what you can think. Which has got the maximum probability? Here, for 3 defectives. As it moves away from that, here at the most, at the left tail, I can go up to 0. It cannot take negative value because it is only the attribute. Okay, attributes cannot have the negative values. So beyond that one, it will go on tapering off. You can just see 6.05. And again, we have calculated 7, exactly 7. That we have calculated 0.0. It will go on tapering off. So perhaps if you calculate probability that it contains 11 defective, it is going to be 0. What this one? Okay. Now what we are interested, what is the probability that it gets greater than or equal to 7, more than 7 defectives? And all these things, all the 6, which works out to be how much? 0.967. This works out to be 0.0329. 0.0329. 7 or more than 7, all these things will have only to the effect of 3.2% to 3.29 or 3.3%. All 7, 8, 9, 10, 11, like that, 12, something like that. Is it understood? So we have to go a long way like this. This is one way out. Another thing, is there any shortcut way of calculating this? That one is, can we approximate? Because how much time it has taken, you just observe. Okay. Now, we have discussed, or I might have spent, or I might have explained in one of my previous classes about the different probability distribution. That was the reason probability distribution is to be used when that is most critical. For everything depends on economical things. Maybe it is time or the cost. Because time is also a money. That is what we say. Okay. So generally, what we have said there, if now, what is P? P tends to 0 in the sense it is lesser than usually we take 0.1. Now it is 0.015. P is equal to what? Then 50. It is infinity. That is what we consider. So it satisfies. And if we multiply this one, the 0.015 into 200. So that is going to be 3. That means its mean value is 3. That is what has been explained. So in this case, it can be approximated by the Poisson's distribution. Then how can we use it? It will be much simpler compared to the binomial distribution, which naturally what is given, it follows the e to the power minus lambda, lambda to the power x divided by factorial x. X is the number of defectives, e is the natural logarithm, and lambda is average value. We know n as 200, p as 0.015, so that is 3. Okay, it becomes easier. You can refer the table also, and we can find out. So compared to that one, it becomes much more simpler. But instead of using just like that individual values, if we refer the table, G table, which gives the cumulative probabilities of Poisson, which follows Poisson distribution, those cumulative probabilities have been given in the table G. Table G. Okay, that means let us see what it consists of, how it looks like. So table G, if you refer, it has got the first one. This is okay. Okay, these tables are provided. Okay, as I told you, control charts, those things are provided, and statistical tables means it will consist of the normal distribution table, the B table, that means all that D2, C2 and other things, those things will also be given provided to you. That is what we have used in the previous classes. And we didn't have an opportunity to use G table. That is what I am using now. Okay? So, the first column, this is what? This is here it is 0, 1, 2, like that. 3, like that it will go on. Okay? Maybe it will go up to 25 to 30 when the NP value is something around 30. But normally it will not cross beyond 15 NP. Okay? Because as this value C prime, it goes on increasing up to 30. Okay? Up to, say, for example, 15. NP value is 15. So, maximum number of defectives we can find out could be around what it means. So, these columns. So, here it starts with 0.02. NP value is 0.02. You just okay. If it is lesser than that, then we can substitute in the equation and try to find out. Okay. NP value is 0.02. When its average number of, that is what NP value is 0.02, and we are interested in finding what is the one. That much is assured any value. And the same thing, probability that it contains don't be under the impression that probability that it contains exactly one defective when the average number of defectives 0.02 is 1. Don't be under that impression. This is the cumulative. That means it contains 0 defective as well as 1 defective. Summation table it is. Exactly 1 defective means if I want to find out, it is 1 minus 0.980. That means it is 0.02. Exactly 1 defective. But cumulative is 0 plus this one, whatever. So it becomes more clearer if I write those things. That is why I have reproduced a part of this table. Let me take up the second one, point. That is and here. That means at the most it can contain 2 defectives. At the most. So probability that it contains 2 or less than 2 defectives is 1. Probability that it contains 1 or less than 1 defective is 0.99. Exactly 1 defective is 0.99 minus 0.961. Or exactly 2 defectives is 1 minus 0.99. That is 0.001. That is how it should be read. Okay, that is the crux, because this is a G summation table. Because of those things, that is what I told you. Whenever we come across greater than or equal to, then or less than or equal to, or equal to, these things can be found out using this summation tables. Likewise, there are the tables for binomial distribution as well. But those are not being provided. Because you might start thinking, why only for the tables have been produced for Poisson distribution, why not for binomial? Yes, they are there. The answer is yes. But this one mostly used because of rare events. That is why it is those tables have been provided. Similarly, what is that we want? Because it is in steps of afterwards 0.15. Steps of 0.15, 0.2, 0.3, like that, it will go on. And for NP is equal to 3, up till what it will go? It will go up to NP is equal to perhaps 15. That is what I told you. Okay. If now in our case it is 3, so under NP value 3, under 0 this is 0.05, 1, 199, 0.199. So I'll use only after the decimal point. 423 multiplied by 1000 things, that is what I am using now. 647, 815, 6, 5, 6, 7, 8, 9, 10, 5, 4 I have written, 5.916, that is 6, 9, 7, 8, 9, 6, 9, and 10, 1.00. So this is 6, like that. So what does it mean? Because it stops here. What does it mean? 10, it stops. Because if the average value is 3, then the probability that it contains more than 10 defective is almost 0. That is what it means. You don't find 11 defective, 0, almost. So even if you substitute in the equation, you will try to find out that. What this one, that is what it means. Now, how do we calculate the probabilities from this table instead of using the binomial distribution? Now I want exact probability that it contains 7 defectives. That is what I want. X is equal to 7. But if I refer this table, if I read, I'll go to this one C prime or NP, so I'll go up to tracing up to 3. NP is that is P into N. P is 0.015 and N is 200, so it will give us 3. So this one I'll go 7 defectives, I'll go to that 7th column. I find out 0.988. This is 0.988 is what? Well, actually it is given 988, but it should be divided by 1000. Because otherwise 0.988 time, that is why it has been expressed multiplied by 1000. So actual reality it is 988 divided by 1000. That is what we have to read. Okay, this is what is cumulative probability. That means what? It gives us this value. It is whatever is given is probability less than or equal to 7 means it can go up to only 0, not lesser than 0. No, it cannot take. that value. Random variable, if it is a discrete in nature, it will not take an integer value, it has to take only integer value and it cannot take up the negative value. Try to understand this. So that means less than or equal to 7, it will vary between 7. That means provided that it contains 0 defective, plus 1, plus 2, plus 3, plus 4, plus 5, up to 7. This total is, it is 0.988. But I want exactly 7. How do I find out? Okay. Now if I look at the value 6 under that one, what is this? It gives less than or 6, it gives 0.96. What this one? Now if I take the difference, that means what is that value? Exactly 7, because it is going to take up only the integer values, not in between values. Try to understand. So exact 7 is what? This one, less than or equal to 7 minus less than or equal to 6, it has to be only 7. So 7 will be, that means x is equal to what? Probability that it is less than or equal to 7 minus. So in this case, it is going to be 0.988 minus 0.966. What this one? So this works out to be 0.022. 0.988 minus 0.966 is 0.022 or approximately 2.2%. But when we calculated by the binomial distribution, what value we got? The product that it contains exactly 7 defectives, we got it as 0.02 or 2%. There is not much difference. How fast we could calculate, you just see. Okay, is it understood? This is how the table is to be made use for. Okay. Now again, how do we calculate? Because this value we have found out to be adding up all these things and deducting it for 1, almost we got it as 3.3%. Or to be precise, let us see what is that we are going to get. Probability that, now what I have to find out? Probability that it greater than or equal to 7 means 7 is included. That is what we need to find out. Okay? That means this one, if I want to find out greater than or equal to 7, then how I'll go? I'll go again complementary way. 1 minus probability that x is less than or equal to 6. That means probability that p is greater than or equal to 7 is exactly equal to 1 minus probability that x is less than or equal to 6. Complementary event, that is what I had explained in the previous place also. That is why we have added it up to 6 only. You can just see. So directly if I refer this table, I can get here 0.9. What is one? 0.966. Directly I can get. So 0.1 minus 0.966. How much it was out to be? 0.034. Very simple. We got almost there 3.3%. Here we are getting 3.4%. Not much different, not much error. How fast we can do it, you just see. So this is how this problem could be solved. And in the process, you have learned how to refer the G table or the Poisson table as well. Okay? Is it understood? Now, if you have understood this one, because this one, I feel I had left it in the middle yesterday and I could not proceed further. So I thought it is better to explain today. Okay? This is how it is to be calculated. So I'll take problems now and then we'll march ahead. Intentionally, I am not telling you under which control chart, because I have already mentioned about the different control charts for attributes. There are 4 types. One is P chart, another one is NP, another one is C, another one is U chart. These things we know and their control limits. Okay. Now we are studying the application part of that. Let us take another problem. Okay. So this will throw some light. Okay. Just take down this. In a manufacturing process, the number of defectives found in the inspection of 15 lots of 400 items each are given in the following table. So we'll take up this one. There are 15 values. This one we can say day wise, or the numbers we can say day or weeks or whatever it is, and the number of defectives. Or you can say it is serial number or sample number 1. Sample. Also we can say like that. So like that we have got 15 values. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. If you look at the first sample, it is 2, 5, 0. What are these things? Number of defectives. 250, 14, 30, 10, 18, 860, 306. Got this one? These are the number of samples taken on different days. And each time, what is the sample size? Sample size is 400. Out of 400, these are the defective. What is the defective file? Found 2, 5, 0, 14, 3, 0, 1, 0, 18, like that for 15 days. What is to be done? Determine the trial control limits for the appropriate control chart and state whether the process is in control or not. That means trial control limits you need to find out. Trial control limits. Find out the trial control limits find out trial control limits and state whether the process is in control or not. That means you need to compare. After finding out the control limits, you compare them with the existing one. That is what it means. Okay. Next one, part B, he says, because I am going a bit slow intentionally, because instead of solving several problems, it is better to solve few problems with proper understanding. Okay, that is what I am aiming at. B, what will be the new value of mean fraction defective if some obvious points outside the control limits are eliminated? Full point. What will be the corresponding upper and lower control limits? Examine whether the process is still in control or not. Because what we need to do is, we need to understand the problem fully. Okay? In a nutshell. We need to have that comprehensive things first in our mind. Then try to answer. So you have to go through the question totally and then try to analyze that one. What is that he has done? He has given here, simply it boils down to a manufacturing process is going on and it produces in a lot of 400 units. Okay? And all these 400 units are inspected, and or the sample size, it consists of 400 units. They found out these are the different, for 15 shifts you can say, 15 samples you can say, 15 days you can say, whatever it is. Let us not bother much about it. Okay? Likewise, these samples are taken. So this is sample number 1. What is the number of size of that sample? That is 400. Sample number 2, again 400. It remains fixed. And when 100% inspection was given, it contained so many number of defectives. That number of defectives, you can see that it goes on varying. It goes on varying from 0 to, it can go up to 18. Just you see. Is it allowed? That is the next question. If all were 0, no problem. If all were 2, no problem. If all were 4, no problem at all. Okay? Or 3, no problem, like that. But some are more, some are less, some are extremes, something like that. Under these circumstances, just like that, we cannot take the decision. But at the outside, it appears to us that there is some variation. Say, for example, 18 here. Is it not more? 14 here. Is it not more? Now these things, 2, 5, 0, 3, 1, 6, 3, 6, something like that. It appears to be something normal. Even 6 might appear to be these things, abnormal. 8, but 18 and 14 at the outset, it appears to be abnormal behavior. That is what he says here in the part B. What he says, what will be the new value of mean fraction defective if some obvious points outside the control limit are eliminated? That means when I find out the control limits by using this data, he expects that some of the points will be falling outside the control limits. That is the clue he is giving. That we need to understand. That is why he has said trial control limits. Because first we need to establish the trial control limits, and then how to establish the standard control limits, we'll see. That is why I have taken up this example. Even though it is simple, but we can learn many things from this particular example. Okay? So now what we'll do, which chart is to be used? What is this? Now it depends on what? Two things. What are the things given? These are the number of defectives, not defects. Okay? So number of defectives. That means either I can use P chart or NP chart. Okay, but which one is more appropriate? But definitely here you cannot use C chart or U chart. Don't say if you use C chart and U chart, because if you just look at this, the things will appear to be same. Got this one? It appears to be same. This is a sample number and it appears to be same. From the outside person it doesn't, because if he goes through the entire problem, that is why I am telling you, we need to analyze the problem first. Then the other things need to be followed. Okay? Number of defectives he has given. So we will boil down to either P chart or NP chart. If it is P or NP chart, best way is simple this thing, you can close your eyes and go for P chart. No problem at all. That is right. But then fraction defective and other things will come into picture. Instead of that one, why I should not use the full values, which will be more appealing practically. The fraction defective is so much 0.1, the people may not understand. Hey, there are 2 defectives, 3 defectives. Okay, fine, like this, here's one. I can understand. Okay, because sometimes we need to convince the people also. Okay, that is why we need to think P or NP chart, right? P always better. But here, since the sample size, it remains fixed. Namely, in this case, sample size is 400. Okay, earlier also, whatever the problem I had taken up, it was 200. That is why the sample size, from sample to sample, it remained fixed. That is why we had gone for NP chart. Here also, we will go for NP chart. The appropriate control chart is NP chart. Okay? I will stop at this point because already the time is up. So NP chart is to be used, and what are the other inferences we have to get, we'll see in the subsequent class. Okay, thank you.